measure a network. So just to give a sense of what I've drawn here, you have k input ports, and at each input port you have n virtual channels with an input buffer. This is really just a FIFO. And you have some logic to do route computation. So when a packet comes in, the first part of it, the head flit, will say what its destination is. And using that, I can determine what my output port should be. Once I've determined my output port, I'll request a virtual channel from the downstream router to send to. Again, due to head-of-line blocking, I would want to be able to pick from a number of virtual channels to go to. So that those need to be allocated. I can't allocate them to simultaneously. Once I know which virtual channel I'm sending to downstream, I need to allocate a cycle to traverse this switch. So that's the switch allocator. Will say, okay, for all these input ports that want to send to all these different output ports, which one gets the chance to send? And then actually do the switch traversal. This is just crossbar, which connects all the inputs to all the outputs. Notice that I've drawn this. There's one access for each input port, even though I have potentially multiple virtual channels. You could imagine I have this virtual channel and this virtual channel both wanting to send to different output ports. Why shouldn't I allow that to happen, right? By drawing it like this, I've said I only allow at one time one virtual channel to send across the switch. And the reason is that, like, absolutely, you may actually want that ability to speed up across the switch. But the thing is, I'm limited no matter what by this bandwidth. So if I doubled the bandwidth across the switch here, it's still an unsustainable rate, just because whatever comes in is at that rate no matter what. So this is the general diagram of the router. And I've drawn at the top this 5-stage pipeline. The idea is that at each cycle, I'm going to do something with an element of a packet. And so the first thing that comes in is this head flit. And I go through this pipeline where at the top, the first thing I do is a buffer write. It comes in and I write it into the FIFO. Then, assuming the FIFO was empty, so the idea of buffer write is that I determine which virtual channel is this intended for, and I write it into the correct buffer. At the next cycle, I'll do route computation. I'll determine which output port does it need to go out on. The next cycle is virtual channel allocation. So I'm going to determine which virtual channel of that output port I'm going to go out on. Then switch allocation, get time on the switch. Switch traversal, actually go across the switch. And then link traversal, that's to actually go downstream. And the idea of it being a pipeline is that while I'm doing switch traversal of the head flit, I can do switch allocation of the next flit after that. And this way I'm sending them along in successive cycles. There's a lot of tricks here that can shorten the pipeline. And the idea is that this dominates, like the length of this pipeline is what dominates the latency of your packet, right? For every hop, you have to pay this cost. And as you see, link traversal I've drawn as one cycle. That's pretty typical. Link traversal, again, on a chip, your links are pretty short. So the cost of actually propagating from router to router is not much. The majority of your cost is actually inside the router. So how you optimize that is really central to getting good performance out of your router. So one trick is what's called look-ahead routing. And the idea is that instead of doing my route computation once it arrives, I'm going to do route computation for the next router that it's going to go to. So that when the flit arrives and I write it into the buffer, I'm actually immediately ready to do virtual channel allocation because the previous router figured out which output port it goes out on. That's the thing that I need for virtual channel allocation. I need to know which output port to go out on. And as soon as I've done a route computation, I can do that. If that's done ahead of time, then I can do that immediately. And then I can do route computation for the next hop during any of these cycles, right? I'm free to do that. One key thing I didn't point out, but I only need to do route computation and virtual channel allocation for the head flit. That's why you get that bubbling, because all the bodies and tail flits go to the same destination. I don't need to recompute that. But so for look-ahead routing, I've shaved a cycle off my pipeline by doing the routing ahead of time. Another trick is speculative switch allocation. So in addition to look-ahead routing, what I've done is I'm speculatively allocating time on the switch, saying I'm likely to probably also have gotten time on the virtual channel. Gotten the virtual channel that I'm supposed to send to. So the idea here is that in the common case that my router is not very heavily utilized, I don't have a lot of flits competing for the switch. Why do I wait 2 cycles doing virtual channel allocation then switch allocation when it's probably pretty likely I can do them simultaneously? The downside here is that I can speculate and be wrong. I don't get virtual channel allocation. There's some competition, and doing switch allocation is a waste in that case. The real thing to do here is that you can do this, you can prioritize. Say non-speculative switch allocations will get priority over speculative switch allocations, and then you're no worse than this case up here. There are further techniques to bypass the buffer in cases. Sometimes you can do switch traversal speculatively as well. So if there's nothing on the input port, none of those were implemented by me, but they are techniques that people use. I'm getting a bit more into the nitty-gritty of how some of these things are implemented. So just to go back actually for a second, how you implement the buffers is not very interesting. They're pretty straightforward. You basically, it's a FIFO. You keep track of pointers into the buffer and write things in. How you implement a switch is also not very interesting. It's really just circuit design. Route computation is also relatively trivial. And I think the most interesting things are allocators. And so I'm going to talk about real details of how you build allocators, what the different trade-offs there are. And to do that, I'll first talk about arbiters. So an arbiter is going to mediate access to a shared resource, one shared resource. So I have lots of things requesting access to a resource, and only one of them can possibly be granted access to the resource. It's a pretty simple idea. And I implemented a fixed priority arbiter. The idea is here I have 1 bit for every agent that's requesting access. Right now I've sort of abstracted this away from the idea of a router. This is just a general piece of hardware you would want to build. N things requesting access, and I want an encoding of which one won. And the way I do this is I basically have this carry line come in. It looks a lot like an adder, actually. So if R0 is requesting, because the 1 came in here, I grant access to it, and no one else gets a carry down. And so if anyone was granted access like above, then all the things below cannot possibly win. And I've drawn here the critical path. At the worst case, it has to go through all of these to set the value. And typically, this is where these allocators and whatnot are what take the most logic. And so you care not just about number of cycles, like with the pipeline, but how long is a cycle. And that's dependent on these critical paths. So a fixed priority arbiter, one of the problems you have with it is fairness, right? I'm always going to grant R0 over R1 every single time the way I've designed this. There are plenty of other techniques, round-robin arbiters and tree arbiters I've seen. This is a simple one. There's lots of techniques to shorten this critical path. You can use use carry look-ahead techniques like you would with an adder as well. Yeah, do you have a question? Yeah, so you somehow have to feed in the carry, basically, to all of these individually. It's significantly challenging yeah. The issue is you need to both carry through, but you also need to be able to set which one starts. Yeah. Though what's typical is a round robin arbiter. Yeah. So an arbiter is a piece that we'll use to build an allocator. An allocator is just one step further. I have many things requesting access to many resources, as opposed to an arbiter, which was many agents request access to one resource. And the kind of allocator I've implemented is called a separable input-first allocator. So I've drawn this matrix, right? The circles are agents requesting access to these resources, right? Where, again, the agents may be a packet requesting access to a virtual channel, or input port requesting access to an output port for switch traversal. And so here I've drawn these 4 agents requesting access to 4 resources. And separable input-first allocation does it in 2 stages. First thing it does is for each input, I pick one that's going to win. And again, this is just that's an arbiter, right? I need to pick, for each of these rows, I pick one that wins, which is, again, fixed priority arbiter, what I use. Once I've done that, on each column, I decide one that wins. And so the end result here I get is these 2 have one allocation to those 2 resources. What you can see here is that this isn't optimal. You might say, why didn't agent 2 get resource 3? Nothing would have prevented it. And indeed, that's one of the downsides of a separable allocator. It's called input first, by the way, because I first do arbitration on the inputs, then outputs. You could do it the other way around. There are other techniques people have used to get better at matching quality, and that's a concern. But those tend to be more complicated and take more power, more area, and so you would generally avoid that. This is pretty typical. So I'll talk real quickly. Virtual channel allocator. So I said there are 2 purposes of virtual channels. One is that I have a virtual channel set for each message type, right? The high-level protocol, and those are unique. And so because they're unique, I can actually have a separate allocator for each one. I'll never have something that's requesting either this message type's virtual channel or that message type's virtual channel. Everything's going to be the same. The other detail is that because of the routing, I only have one possible output port I can go out on, and all the packets of that message class go out on the same, could go out on any virtual channel. It's just for head-of-line blocking. So I just use the separable allocator that I showed before for each message class. The switch allocator, perhaps a little easier to visualize. I want to generate matchings between the input virtual channels that are ready to send and the output virtual channels that have space downstream. And what I do is at each input port, I'm going to pick one input virtual channel that's going to request switch traversal. Because again, the way I've drawn, back here, I can only send one virtual channel at a time. There's no point in saying multiple of these can try to win. So I pick one of them that's ready to send. And then at the output port, I pick one of the input ports that had something ready to send and send to that. And that sends things through. So again, this is not an optimal matching because you could say, why why can't I potentially send, I may have multiple input VCs ready to send, but due to the design, it's not optimal. And